Swayam Prabha. Digital India. Educated India.
So far we have discussed the ideas related to scalar product or the dot product. Let me now quickly introduce the concept of vector product. Vector product. So suppose my vectors A and B, are the representations of the position vectors OA and OB as usual. Okay, and let us say that I have n. Let n be the unit vector which is in a plane perpendicular to OA and OB. Unit vector perpendicular to a plane OA and OB, and we see that we have two vectors A and B, and we have the unit vectors n, right? N. So this is OA and OB, this is the unit vectors n. Okay, so then we can quickly define the scalar product not the scalar product this time, but the vector product. A cross B is given by magnitude of A times the magnitude of B times sine of theta, and again theta is O is this, so theta is the angle between A and B, and this is along the direction n. Notice now that the vector product is the result of the vector product gives us a vector. The result of a scalar product or the dot product gives us scalar, right? So the moment we have a vector, the vector must have a direction, and the direction is along the vector which is in a plane perpendicular to both the starting vectors A and B, right? So we call this vector set ABN as a right-handed system, right-handed system, which means that A cross B, if these are A cross B will be a vector along the n direction, or B cross A will be a vector along A direction, and so on, right? So that's the right-handed system. And now we have some results based on this right-handed system. The set of results says that A cross B, if listeners can quickly recall that when we were taking the dot product, then the order of the dot product of the vector did not matter. That is, A dot B was equal to B dot A. But this time A cross B is minus B cross A. So the moment you change the order, you will introduce a sign which is the negative sign. And then we have, so I would call this first result as anti-commutative. The scalar product was commutative. And now we have the so-called distributive law. A cross B cross C will be A cross B plus C. So the distributive law says that this is equal to A cross C plus A cross B plus A cross C, right? And that is my distributive law. And then what I have is that the scalar multiple of A, the scalar multiple of A cross with B is given by lambda times A cross B. The scalar multiple of A cross with B is, we can take this lambda out and we can first take the cross product. Okay, and then another trivial result is the cross product of a vector with itself is going to give you 0, because the vector is aligned with the same, along the same direction. So the angle between these two vectors is 0. So sine of 0 is 0 in the formula of the cross product. So then we have that if the cross product of two vectors is 0, so if we have this cross product to be 0, then either A or B is 0, either this is the case, one of the vectors is 0, or we have that A is parallel to B, or anti-parallel to B. The moment you have parallel or anti-parallel, for parallel the angle between A and B will be 0, and anti-parallel it will be 180 degrees, and in either case sine of that angle will be 0. Okay, so then suppose coming back to this these set of properties and applying them to our standard basis function. Standard basis in 3D, this is I, J, K. What is the standard basis? This is the set of three vectors which are of magnitude 1 and they are orthogonal. So we can quickly check that I cross J is going to give us K, and then you have K, well, J cross K is going to give you I, and we have what else? J cross K, and then K cross I. K cross I is going to give us J. Okay, so that those are the various permutations. If you reverse the sign of any of these cross product, then if you reverse the order, then you will introduce a sign that is a minus sign on the right hand side. Okay, so so now in terms of finding the cross product of any vectors, for example, if you are given the vector A to be in this form, in the standard basis function form, this is lambda 1 I plus lambda 2 j plus lambda 3 k, and B is mu 1 I plus mu 2 j plus mu 3 k, and we see that A cross B is given by A cross B is given by the determinant I j k lambda 1 lambda 2 lambda 3 and nu 1 nu 2 nu 3. So essentially to find the cross product of a vector of arbitrary dimension, we set up this determinant, and then we start to find the individual component, we start to find the adjoint for the corresponding components, right? And that is how we calculate the cross product. Now then, so far we have introduced both dot and cross product. Let me quickly also introduce the scalar triple product or the triple product. So again, this is mainly, I am just recapping all these ideas because these are the ideas we don't want to come back when we do some of the more complicated problems in the later modules. So the scalar triple products. So we see that the scalar triple product or the triple product will have the following properties. Eventually we are going to list how to find the scalar triple product of the vectors. Well, as the name suggests, triple, which means that this sort of product will involve three vectors, right? So we have vector A, B and C, and the triple product is the combination of dot with cross. So that is A dot B cross C, that is the scalar triple product. Sometimes we denote it as this square bracket A, B, C, right? Let me put a comma as well. And then we see that A dot B cross C is given by A cross B dot C. So So here is the first result says that the cross and the dot can be interchanged. So that is the result. So interchange dots and cross. Okay. So then what we have is that well, the next result says that A dot B cross C is also equal to C dot A cross B. Basically the permutation. So C A B, and then the next result is B C A. So B C A. Okay, so all these three permutations are equal, and then so we call this as cyclic permutation. We call this as cyclic permutation. Okay, and then the third result says, let me remove this. The third result says that suppose the scalar triple product A B C is 0. If the scalar triple product is 0, then A, B, C are coplanar, right? Why? Because if the scalar triple product is 0, one of the two of the three vectors will involve a cross product, and since they are coplanar, right, the coplanar is going to give us a vector which is aligned, which will be aligned in a coplanar. The cross product will vanish in that case, right? So that is the whole idea. So now, yeah, so if A, B, C are coplanar, or any two vectors are 0. Any two vectors are 0. So then the next result says that suppose this scalar triple product is positive, then we have a right-handed system. Right-handed system means that if we follow right-handed system. So what it means is if we follow the cyclic permutations, then the values are equal. If we break the cyclic permutations, then we will introduce a minus sign, right? And if it is less than 0, then we have a left-handed system, right? So left-handed is the opposite of right-handed, which means that whatever permutations you have taken in right-handed, you reverse that. Okay, and then finally the last result gives the actual formula for the scalar triple product. So suppose we have A, B, C, and each of these are vectors with components AIs. This is vector with component BIs, BJs, and this is vector with component CKs, right? And we see that this is also equal to, the formula is that this is going to be the determinant A1, A2, A3, B1, B2, B3, C1, C2, C3, and we have that this is going to be the determinant, right? Okay. So so that is my triple product. Okay, fine. So then what we have is, let me continue with some quick examples. The first example is that we need to expand this result A cross B dot with C cross D, and we see that this is equal to A dot with B cross C cross D. And well, what we have done is, here we have used the interchange of dots and crosses. Interchange of dots and crosses. Interchange of dots and crosses, right? And then what we can do now is, we can now expand this this set of cross product. This cross product is going to be A dot with, now this quantity inside the bracket will be B dot with C, B dot C, B dot D times C minus B dot C times D. So this quantity is in the direction C of C and D, right? And then we can quickly take the dot product with A outside, and we can see that this is B dot D times A dot C minus B dot C times A dot D, right? And that is what we have. Fine. So that's what we have in terms of the result. Then we can quickly talk about, so we have so far talked about vectors, right? So let us now make a progression to talk about vector functions. Now it could be vector functions of scalars, that is the argument being scalar, or vector functions of vectors, right? So that is something we have to clarify. But to begin with, let us talk about the simpler of the two, that is vector functions of a scalar. Okay. So we talk about vector functions of a scalar, vector functions of a scalar, and we see that suppose the vector v is given by v of t. So my t is my scalar, which is the argument. So this is my scalar. Okay. So let me call this in a more general format, that this is my alpha. So we can talk about, let's say typically you have vector functions in the form of velocity. We are going to introduce all these ideas in a short while. Or we can have acceleration and so on, so and so forth. And we can talk about derivatives of vector functions by the following limit: dv d alpha to be the limit alpha going to 0, delta alpha going to 0, v of alpha plus delta alpha minus v of alpha divided by delta alpha. Okay. Okay. So then what we have is, we can quickly look at some of the properties of derivatives. So derivatives are linear operators. We have that the derivative of u plus v is u dot plus v dot. When I say dot, it means that this is the derivative of u del alpha, and this is the derivative of del v del alpha, right? And similarly, the next property is derivative of lambda u is, we can see that this is going to be lambda times derivative of u with respect to alpha plus u times derivative of lambda with respect to alpha, because we need to differentiate the scalar as well, right? And then we can similarly differentiate the dot product of two vectors, u dot v. So this is going to be u dot with the derivative of v plus v dot the derivative of u. Okay. So that's the quick set of properties. And now let us start with the general ideas of position vectors and do some algebra and find some other quantities of interest. Okay. So what have we got here? So we are let us start with some small example as to the ideas we are trying to introduce. So the problem says find the position vector of a particle. Remember, now rather than talking about a point, we are going to talk about a particle, a live particle which is moving, right? Moving with respect to time. So time being the scalar, right? So suppose a position vector of a particle r of t, r is the position vector, is given by 2t square minus 5t I plus 4t plus 2 j plus t cube k, right? So we see that this is my position vector. The problem says find dr dt and dr d2r dt2. So we need to find the rate of change of the position, which is the velocity, and the rate of change of the velocity, which is the acceleration. And this will involve a quick and dirty differentiation of this position vector once and twice. Okay, and that is going to give us the result. So then here is one quick example, another one. So suppose I am given a vector which is in the form a, which is a function of the scalar a of t, and now the next vector b is a constant vector. Then we need to show that the derivative with respect to the parameter t of the triple product a dot with a dot cross b, right, is going to be a dot with a double dot cross b, right? So we need to show this. We can quickly, again, because this is a dot product of two vectors, we can use our dot product results, that is the the distributive results, that this is going to be a dot with a dot cross b plus a dot with a double dot cross b, and then the third result will involve a derivative over b, but the derivative over b will be 0 because b is a constant vector, right? So I am not going to write the third term, which is 0. Now notice that this quantity I can interchange my dots and crosses, and this is going to be a dot cross with a dot with b, right? Interchanging the crosses and the dots, and we see that a cross a is going to be 0, and that is going to cancel this quantity as well, and we get our result, which is what we had to show. Okay. So then, so these are all the quick examples. Let me now introduce the concept of tangent vectors, normal vectors, curvature, and so on. So let me talk about tangent and normal to a curve. Tangent and normal to a curve. So what have we got is, suppose we have a curve. So this is a curve. Let us say we are talking about a curve S, and we have a chord which joins the curve. Let us say this chord is joining the curve A and A prime, right? So this is my chord which joining two arbitrary points on the curve. Now the moment I start to allow A prime going closer and closer to A, that is, I start to shift my chord, that is A double prime and A triple prime. I start to shift my chord in such a way that A, the first point, is going closer and closer to A, then the resulting chord that I have is now going to be eventually touching the curve at point A, and this resultant curve is going to be my tangent to the curve at point A. So that is the geometric meaning of the tangent, right? So what have we got is, so suppose we have a chord AA prime, and this is going to be, let us call this as delta R. This is going to be delta R. So this is R at alpha plus delta alpha minus R at alpha, so the chord AA prime, and we see that the unit tangent defined from this chord, the unit tangent, it is going to be a vector. The unit tangent vector defined from this chord is going to be let me denote this unit tangent vector to be T of alpha, or well, I don't want to use small letter, so this is capital T of alpha, right? So T of alpha is going to be will be delta R, and since it's a unit tangent, I divide it by its magnitude, which is the magnitude of delta R, right? And what I just said is that the chord is going to be slowly going to shift in such a way that the point A prime starts to shift to A, right? So now I have that this is limit delta A goes to 0. So when I start to shift, so you can see that the position vector of A prime is R alpha plus delta alpha. So when we take limit delta alpha going to 0, we see that this is the case, and we have that this is delta R, and I have that this is my definition of the unit tangent vector. Okay. So the moment I introduce this this limit, I see that this is going to be so let us from here let us find an important derivative. So note that dr d alpha. What is dr d alpha? So dr d alpha is limit delta alpha going to 0 of delta R by delta alpha, right? Alpha is the scalar argument and R is the position vector. The change in position vector is also equal to limit delta alpha going to 0 times delta R by delta R times delta R by delta alpha. So what have I done? I have used, I have introduced magnitude of delta R in the denominator and in the numerator. And notice that this quantity is what? This quantity is my tangent vector, and what is this? Delta R over delta alpha is nothing but the magnitude of dr d alpha, right? Alpha is a scalar, so I don't mind putting a mod or an absolute value over delta alpha as well, because alpha is a scalar. The change is also going to be a scalar. So this is the magnitude of dr d alpha, or this is going to be, so what have we got is that R prime, when I denote prime, I denote that prime denotes the derivative of R with respect to alpha. So the prime denotes the derivative with respect to the scalar argument alpha, and R prime is the tangent T alpha times R prime mod, right? Okay. So what have we got here is, that the unit tangent vector T alpha is going to be the derivative of the position vector with respect to its argument divided by the derivative of the position vector with respect to its argument mod, or the magnitude from this result, right? Okay. So what have we got here is, so that's the formula for the tangent, and from here we can derive the special case when suppose our parameter alpha is the arc length of the curve. So what have we got is, so this is the special case. So suppose my parameter alpha is S, which is the arc length of the curve, right? So we see that in this case dr ds, The parameter now is S, right? A is nothing but limit delta S going to 0, delta R, delta S. But notice that delta R is the length of the curve from point A prime to A. It is the length of the curve. But the length of the curve is nothing but delta S. It is the arc length. Length of the curve on the curve will be the arc length. So this quantity is nothing but 1, because delta R mod is absolute. The magnitude of delta R is the same as the magnitude of delta S, which is delta S. So this is going to be 1, and now in this case I can say that my unit tangent vector, when the parameter is S, the arc length is nothing but R prime of S. So if we have the special case where the parameter, the scalar parameter is the arc length, then we don't need the magnitude. The magnitude is here, the magnitude of this quantity is 1. That is what we found, right? So this is another way to find the unit tangent vector. Okay. So far we have looked at what is the tangent vector. Now let us try to find the normal to the curve, right? So unit normal. Okay, so now we have the tangent vector T of S, right? So this is my tangent vector. This is a unit tangent vector, which means T of S dot with T of S is going to be 1 unit tangent vector. Or we see that d ds T dot with T is going to be, well, we can use the chain rule. This is going to be 2 dt ds dot with T, right? It's going to be this, and of course when we take the derivative with respect to S, we expect the derivative will be 0, because on the right hand side we have 1 constant. So now what we have got is that a quantity which is the tangent dot product with another quantity which is dt ds gives you the 0. So which means that dt ds is perpendicular to T, the tangent. I mean, not necessarily that dt ds is 0. So that is a special case. But in general, we expect that this is the case because of this result that we found. So which means that dt ds is going to be aligned along the normal to the curve, right? So which means this result says that dt ds is some constant times the normal to the curve, let's say n, right? Normal to the curve n. Well, I think we have been using our small letters for unit vectors and capital letters for typical vectors, right, which are may or may not be unit. So readers should always should not be confused that these are all unit vectors. These are all unit vectors. Okay. So now here is the result. It gives us this particular result. Let me call this as 2. It introduces 2 new concepts. The constant of proportionality kappa is the curvature, is the so-called curvature. And what is this curvature? The curvature is equal to the magnitude of dt ds. The magnitude of dt ds, and n is the unit normal. So when you find dt ds, divide by curvature, you are going to get the unit normal. Okay. So so what have we got here? Let us quickly look at the geometric interpretation of whatever we have just done, right? So geometric interpretation. Okay. So what we are geometric interpretation of the unit normal n and kappa. Well, kappa is a constant of proportionality which is scalar. So notice that suppose you have the position vector of a curve R of S. If we use our Taylor series, our Taylor series along at s equal to 0, right? So if we start expanding our position vector around s equal to 0, we see that this is r of 0 plus s times dr ds at s equal to 0 plus half s square dr d2r ds2, right, at s equal to 0 and plus order s cube and so on, right? So that's the typical Taylor series, and we see that dr ds is going to be this is going to be nothing but the unit tangent vector t of s. Dr ds, I think this is somewhere we have just found in our previous set, that if alpha is s, the arc length, then we have that the unit tangent vector t of s is dr ds. Okay. So now the result says that this is r of 0 plus s of the tangent s times t of s, the unit tangent vector, plus half s square d2r ds2. We see that this is going to be kappa times n. Kappa times n. Why? Because d2r ds2 is nothing but dt ds. So d2r ds2 is dt ds. So that we replace it with kappa times n and so on, right? So we can see that the tangent to any curve is the first approximation, the Taylor series approximation near arc length s equal to 0, and the normal is the second, the quadratic approximation to this curve at s equal to 0, right? So the tangent and the normal are first and the second approximation to these curves at s equal to 0. Okay. So we can typically, there are lots and lots of very simple examples. Given the position vector, we can quickly find the tangents and the normals and the curvature and so on. So that completes the basics that we need in order to start solving some more physically motivated problems related to the essence of this course, that is the mechanics of bodies. So thank you very much. Thank you all for listening this result, and thank you all for listening to this set of 3 modules. And in the next module, I am going to start talking about some basic mechanics, that is starting with the Newtonian mechanics. We will look at some basics, basics now from the physics point of view, so-called inertial frames and non-inertial frames, and how to go about from there. Okay, so thank you all for listening. Thank you very much.